We're going to continue to introduce derivatives today. And we're going to review something first. We talked about this last class. We talked about secant lines. Secant line is a line that connects two distinct points. Of a function. For example, if I have this point here and this point here, we would connect those 2 points to create a secant line. And of course, that line could be extended if we really wanted to. But we can just leave it like that. We have tangent lines. Tangent line, it's tough to kind of give it a formal definition. You don't want to say it just connects your, or just touches your function once, because that is not necessarily true. But you can say it just nicks your function at a point. Just barely touches your function at a point. So like here, right down here, my tangent line would look something like this. It would just barely nick it. Now, if you see, if I extended this tangent line, it would hit my function at a second point. I don't care that it hits my function at a second point. This is the tangent. It is just nicking my function right there. Okay? Now, what the slopes of these lines are very important, and what they represent are very important. So the slope of the secant line, what did we talk about last class? That is. What does that represent? The average rate of change of your function. Okay? If you take the function values, you subtract them, you divide it by the interval, you get the average rate of change of your function. Now, what would the slope of the tangent line represent? Exactly. It would represent the exact rate of change. But instead of average or exact, instead of saying exact, we say it's the instantaneous rate of change. I'll just say instantaneous ROC of f of x. Okay, how we introduced that to you was asked about the exact velocity of this dude at this specific position. We said if we knew the position of the dude a little bit after the time we were looking at and a little bit before, we would create this line. And when we sketched this line, we created what looked like a tangent line, and it is a tangent line. Well, that good approximation, that great approximation, will be the exact velocity of my dude at that point. So this tangent line would give me no longer an average rate of change when we're talking about 2 points on top of each other. It would give me an exact rate of change at a specific point. And that's what a derivative is. A derivative is a fancy math word for instantaneous rate of change. But you know, instantaneous rate of change is also like a fancy couple of math words for just slope of a tangent line. So now we have 3 things that are equivalent to each other. Derivative is the same, let me spell it right because this is, Derivative is equivalent to instantaneous rate of change of a function. And this is derivative of a function, instantaneous rate of change of a function. And that's equivalent to just the slope of a tangent line. They're all the same. I can ask you for one, and you'll know it be the other, which is the other. Now, let's talk about some notation. Notation for derivatives. If we're given a function f of x, I would say the derivative function would be f prime of x. We introduced that last class when I said, oh, the slopes of tangents, this thing that we're sketching, that's f prime of x. I didn't tell you why, because I didn't tell you what derivative meant. I didn't tell you why we're using this notation. This is just the notation for the derivative function, okay? This function gives you function values. This will give you slope values. If I asked you what f prime of 1 was, you would say this is the derivative of f at 1. Sure. You can say that now. But what does the derivative of f mean? The slope of f at x equals 1. And you would say it's the tangent slope. And of course, you know that the tangent slope is the instantaneous rate of change of your function at 1. Okay? So you had some questions that asked you, what is g prime of 1? And you're like, I don't know. It was just asking you, what's your slope of your tangent line to your function g at 1? Okay? So let's pause here. Let's go to our homework. All right. So we know what a derivative means. It's an instantaneous rate of change instead of an average rate of change. It's the slope of a tangent line instead of the slope of a secant line. Now let's see if we can find exact values of derivatives. And change this up, see if it might help. The question is, what is the instantaneous rate of change of the function when x equals 2? Well, first of all, when x equals 2, what's my function value? If my function right here is 2x squared. 8, right? You plug in 2, f of 2 is 8. So 2, 1, 2, 3, 4, 5, 6, 7, 8. Right here. So I could ask you now, what's the instantaneous rate of change of f of x when x equals 2? You know that's the same as what is f prime of 2? Or what's the derivative of f at x equals 2? And you know that's the same thing as what is the slope of the tangent to your function at x equals 2? Okay, well, if I have a calculator, what can I do to find a good approximation of that slope? So it's going to be this slope right here. Was it Miss Wise? Yeah, we can go to either side. I can say, well, let's take a value at 1.999 and let's take a value of 2.001. You know what? I'm actually not even going to do 1.999. I'm just going to use my value at 2 because I already have it. I know f of 2 is 8. And I'm going to use a value just a little bit to the right of 2 because essentially it'll still kind of be infinitely close and it still will be telling me what I'm doing. But that is exactly the right idea. So let's say f of 2.000001. Oh, maybe that's why I changed it to 1. Yeah, should we go back to 1? Let's go back to 1. I'm just thinking about the answer, and the answer might confuse you. This is what I do here. I make sure things don't confuse you that much. We're going back to 1. Switch to the guns. 2 closer missiles. Go here. Maybe next class I'll do 3. All right. So we were still correct though. We are still going to use points really, really close to 1, like 1.00001. And you know what? Just because I don't want to crush my calculator, maybe I'll just put 3 zeros, and that'll give me a decent approximation. Now, let's use our calculator to figure out what that value is. 1.0001. 2.0004. So I plug in 2 times 1.3001 and I square it, and I get 1, 2, 3, 1, close, square, equals 2.0. 3 zeros 4, 3 zeros 2. Hopefully it stops there. Maybe it repeats. I don't know. All right, well, what do I do with those values? Slope formula, right? We're going to use the slope to get a good approximation of my slope. I got a point right here. It's even closer than this. And a point right here. Let's find the slope. So this value minus my other function value over b minus a. And in my calculator, since this is up, I'm just going to go minus 2 divided by 1.001 minus 1. Oops. Second, insert. You guys know how to insert? Good. Enter. We get a number very, very close to 4. Well, what if I add a couple more zeros in this point and then make my 2 points closer? What do you think this value would become if I made my points closer? 4. What is that idea of getting closer and closer and closer to a distinct value, but not actually getting there? It's a limit. Exactly what we're doing. If I added another 0 and I got even closer, we'll be using limits to to estimate slope of my tangent. Well, in reality, what we'll do is if we take this point and we get really, 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 really close to this other point, so that they're essentially on top of each other, what we do is we go from an approximation of my slope value to an actual, I know what my slope value of my tangent is, because I'm talking about taking 2 points so close to each other, they might as well be the same point. But they're not. They won't be the same point. It'll be just that close to each other that it essentially is. And if you take the slope of those 2 points infinitely close to each other, boom, that's going to be your tangent slope. Does that make sense? I could show you, but we need to move on. So let's see if we can generate maybe our how to find a slope of a tangent formula for all situations. What situation are we finding? A how to find slopes of tangents anywhere. For anything. Okay, so I have a function. I'm not going to say it's 2x squared. I'm just going to say it's a function. And I'm going to try to find the slope of this random function at this point x. Now, I know if I'm dealing with a slope, I need the slope formula. And I know that we use f of b's, f of a's, change in my function values divided by the change in my inputs. Well, let's call this point here A, this point here B. This, therefore, will be f of A, and this will be f of B. Just so we can kind of know what to plug in for A. For A, I'm going to be plugging in x. Well, if this is x, this must be the function value f of x, using this x. And what I'm going to do is I'm going to place another point for a secant a distance away from this x. So I'm going to say, well, take and start at this x, and I'm going to add an h distance. And h is a distance. And that gives me what here at b? Just x plus h. Now, if this is x plus h, this function value here is f of x plus h. Well, let's plug in this stuff into my slope formula to find the slope between these 2 points, here and here. Slope equals f of b is f of x plus h minus f of a. F of a is f of x divided by b. B is x plus h minus a. A is x. Okay, just use the slope formula. Now, what happens here? Can we do anything? The x's will go away. X minus x disappears. So now the situation is the slope of this line is f of x plus h minus f of x over h. Well, now this is not a great approximation right now because h is kind of a decent distance. What do I need to do with h so that I get these 2 points to be really, really close together? And I'll get those 2 points that are close together, but what will end up if I extend those 2 values, I would create my tangent line. What do I need to do with that h? Make it small. How small? Really, really small. So small that it's going to be approaching what value? 0. Well, do you want to find the slope of a tangent of any function anywhere? Take the limit as h approaches 0 of this, and you will successfully find that slope. And this formula is the definition of the derivative of a function. Now explain to me where we got this formula from. The slope of what? Yep, but how did we find the slope of this tangent line? We took the slope of 2 points. Ms. Wilkins? Yeah, we took the slope of the secant line, but the crazy thing about our secant line is that these 2 points were what? What did we do with our points? Yeah, that's exactly right. This is the slope of 2 points infinitely close together. Now, I could have done the same thing, but I could have said that this was c instead of x, and this was x, and this would be x minus c. There's an alternate form of this. We won't be using it, but we need to be familiar with it. It's the limit as x approaches c of f of x minus f of c over x minus c. Okay? We just need to be comfortable with it, but today and for your test, you need to be comfortable with that guy, primarily. Now, let's remember this. Notation for derivatives. We have a function and its derivative. A function can look like this. A derivative does not necessarily have to be just values or a graph. There could be an equation that would produce the slopes of my tangents of this function. I'll tell you right now, this derivative is that. So yes, we know that this is a function. This would then be the slope generator function of f. I plug in x values into my function. I get function values out. I plug in x values into my derivative. I get slopes. And we're going to do that for this guy, we're going to find the f prime function, and then we will plug in the value 1 to make sure that my derivative is actually 4, to make sure the slope at this value 1 is actually 4. Now, another key thing to remember is generating lines. Generating a tangent line. Equations of tangent lines. For an equation of a line, I'll need a point and a slope. Now the point will come from my function. That'll tell me where my tangent line will pass through. The slope will come from my derivative function. That'll tell me what my slope of my tangent line is. Let's say I know f of 1 is 2, and I know f prime of 1 is 4. I would say my slope of my tangent line at this point 1, 2 is y minus 2 equals 4 times x minus 1. Where does this come from? This comes from y minus y1 equals m times x minus x1. Now let's do this with a couple of functions. Let's find the derivative function, the slope generator function, for maybe 2x squared. You'll need a lot of space for this. I know the derivative of any function is this: the limit as h approaches 0 of f of x plus h minus f of x all over h. Now I know what f of x is. It's 2x squared in this situation. That's my function I'm going to try to find this derivative function for. Well, let's think about what f of x plus h is. Well, it's just wherever x is, instead, you place x plus h in parentheses. So what was x becomes x plus h. Well, we're now ready to plug in this stuff into my definition of my derivative. So I want to find the limit as h approaches 0 of 2 times x plus h squared minus 2x squared over h. Step 1 of finding a limit. Plug in the value that we have. So let's plug in 0 for h. What happens when I plug in 0 for h? Get undefined. Okay, that doesn't work. Step 2, if I get an undefined value when I plug in 0 for h. Try to simplify. Let's go. Square x plus h. X squared plus 2xh plus h squared. Subtract the 2x squared, that's all over h. Distribute the 2x squared plus 4xh plus 2h squared minus 2x squared all over h. what happens? The 2x squared go away. What can I do? I can factor out an h from these remaining top two terms, giving me h times 4x plus 2h over h. Well, we can cancel that h, and we have a simpler function that I can plug this 0 for h into. And when I plug in 0 for h, what do I get? 4x. Turns out, if I have a function, 2x squared, if you want to know the slopes of the tangents to that function, you plug values into this derivative function 4x. Yep. No, 4x, because we have 4x here when we plug in 0, so this is the function 4x. So what is the derivative of f of x when x equals 1? 4. F prime of 1 is 4. That's not our bell. That is a fake bell. I was about to say, gosh, cut me short. Now, what is f prime of 3? 12. What does this tell me? Mr. Kaiser, what does f prime of 3 tell me? Not the function for the tangent line. It gives me the slope of the tangent line of my function 2x squared when x is 3. This is a slope when x is 3 for f of x. Okay, good. So my derivative at 1 is 4. That means the slope of this tangent line that we were looking at the beginning was 4. We were correct in our estimation and our guess. All right. Well, now let's write the equation of our tangent line that we drew in red all the way up here. Let's generate the equation of this line that we drew. Well, for the equation of a tangent line, I need a point and I need a slope. Where do I get my point from? From my function. Exactly. Where my tangent is located. Well, we're looking at when x is 1, I'll get the y location from my function. The reason why we didn't do this at 2 is because the point and the slope would have been the same. And that would have just blown your minds. The slope I get from my slope generator function, my f prime of function. F prime function. I plug in my x value into my slope generator, my derivative function, and I get my slope. So we get my equation, y minus y1 equals my slope times x minus x1. Now, there's going to be 2 other examples of this process that I will do most likely online by myself that you can see. So go back and watch those because it's really all Unit 1 stuff, like distributing to simplify, multiplying by conjugates, finding common denominators, all that stuff you did in Unit 1, we'll do it again. Okay, and you'll do it for homework. Now let's talk about if there are situations when we cannot differentiate. That means take the derivative, this word. And the answer to this is yes, and I'll tell you why. To have a derivative, this limit, which is the definition of a derivative, must exist. When do derivatives exist? What was that? When the denominator is not equal. No, not necessarily. Let's think about one-sided limits, Kaiser.
The limit from the right equals the limit from the left.
Exactly. That means the left-hand limit must equal the right-hand limit. So that means as h approaches 0 from the right and from the left, those values must be the same. Well, if I talk about h approaching 0 from the left of this, what is this giving us? Where did we get this formula from? Slope. This is telling me that 0 from the left would be the slopes from the left. The slopes from the left must equal the slopes from the right for the limit to exist, which means for the derivative to exist. Now, when do the slopes from the right and the slopes from the left not equal the same values? That's one situation. Whenever we have a discontinuity, slopes are not the same. So, discontinuities, you're not allowed to differentiate at discontinuities. But there are others where we don't have discontinuities, but we can't take derivatives. You saw some on your homework. This graph, this V, at this point down here, this sharp point, the derivative does not exist, or the slope does not exist. Dne. Now, why is that? Because the derivatives or the slopes of the tangents to the left are all negative, and they're all the way negative up until this point, and the slopes from the right are all positive, and they're all positive up until this point. So we can't take the derivative, or we can't say that this has a slope. One more would be at a cusp. This is a cusp. The slopes from the left and the slopes from the right are not the same. You can't take the derivative at that cusp. There is no tangent slope at that cusp. It's not 0, it just does not exist. At that point, the derivatives exist to the left, the derivatives exist to the right, but at that point, the derivative or the slope of the tangent does not exist. All right. I'm going to do those other two examples. Study for your test. All right, let's go back and do the other two examples on the previous page. We did this guy. We found the derivative function for this function 2x squared. Let's now find the equation to the line, the tangent line of this function when x equals 3. Okay, so we just get right to the point. We want the equation of the tangent line to this function at 3. Well, let's first realize that for an equation, I need my point and I need my slope. The point I will get from my function. The slope I will get from my derivative function, my slope generator function. I can find this point immediately by plugging in 3. I get 3 plus 1 is square root of 4, which is 2. Sweet. Now, the derivative function, I do not know, but we need to find it. So we will use the limit definition of a derivative to find it. Limit as h approaches 0 of square root of x plus 1. Sorry, let's start with just the definition. Sorry, limit of f of x plus h minus f of x all over h. And let's make sure we know my function. That's my function. And I'm sure of what x plus h in my function looks like. It'd be the square root of x plus h. Can be in parentheses, but since we're just adding 1 to it, we don't need it. Okay, so let's plug this in and this in into my definition of a derivative. I have now the limit as h approaches 0 of the square root of x plus h plus 1 minus f of x is the square root of x plus 1, all divided by h. Now, I tried to plug in 0. That's my first attempt. I get root x plus 1 minus root x plus 1 over h. I fail, or over 0. I fail. I get an undefined value. So, step 2, attempt to simplify. We remember from Unit 1 that whenever we see square roots in limits, we probably want to get rid of them. And we get rid of them by multiplying by the conjugate. So I will multiply both sides by x plus h plus 1 plus root x plus 1. And down here the same thing, root x plus h plus 1 plus root x plus 1. Now what happens is I'll get this quantity squared minus this quantity squared, which will just give me x plus h plus 1 minus the quantity of x plus 1 all over this nasty denominator, which I will not distribute the h into because it'll just make things more complicated. So I'll have h times root x plus h plus 1 plus root x plus 1, close quantity. Now we will attempt to simplify this numerator. I'll change this to a plus, distribute my negative. My x's will cancel, my 1's will cancel. It will leave me with just an h on the top over this denominator. Boom. Now my h's will cancel, which is what I want to see happen, because now I can plug in 0 into the h's that remain. And I get 1 over root x plus h plus 1 plus root x plus 1. Plug in 0. I get 1 over root x plus 1 plus root x plus 1. That gives me 1 over 2 root x plus 1. What we just discovered was the derivative function for my original function, root x plus 1? I find the slope generator, the function that I can plug in x's to get slopes, is 1 over 2 root x plus 1. Well, I will use this slope generator to get my slope that I was looking for. I found this, so this goes into an exclamation point. I plug in 3. So f prime of 3 would be 1 over 2 root 4. That'd be 1/4. There's my slope. Here's my point. This is an x. This is a y. I can develop my equation. Y minus y1 equals my slope times x minus x1. Leave your answer just like this. It's perfectly okay. Hooray. We found that the slope of this function at 3, that was equal to 1/4, and we found the equation of the slope of this function was this. And if you wanted to graphically see it, you would know that x plus 1, we'd be talking about a graph that would kind of end at -1 and go out like this. At 3, right here, we can see the slope would be shallow, and the slope would actually be equal to exactly 1/4. Okay, so it all goes back to Unit 1 stuff, multiplying by conjugates, simplifying, being careful, showing every step to get your answer. Now this is just asking me to find the derivative. I could ask you this multiple ways. I could say find the instantaneous rate of change of my function at a point when x equals 3. Anything. I could ask you whatever I wanted to. You should know that they're all interchangeable. I could say find the slope of the tangent. Of your function at this value. But right now it's just saying find the derivative of this function, and I'm going to throw in at x equals 3. Well, that means I need my slope generator function, and then I'll need to plug in 3 into it to see what my slope is of my original function when x is 3. Well, let's find this derivative function using the limit definition of a derivative. We get f of x plus h minus f of x all over h. Now, this is f of x. Let's make sure we know what f of x plus h would look like. That'd be 2 over x plus h plus 3. Now, be careful when you plug in x plus h into x. Make sure it's going in parentheses. So if it's being squared, it's x plus h quantity squared. If it's just in different locations, you have to really account for plugging in this x plus h. Make sure you do so using parentheses in most cases. All right, let's plug in our function and this guy into our limit definition. We got limits as h approaches 0 of 2 over x plus h plus 3 minus 2 over x plus 3. Try to be neater. And I'm going to divide that all by h. However, that's going to get messy. I'm therefore just going to say, hey, let's multiply everything by 1 over h. Okay, but don't forget about it. It's still here. Now, I can't plug in 0. If I plug in 0, I get 2 over x plus 3 minus 2 over x plus 3, that's 0. This would be times 1 over 0. 0 over 0, undefined, fail need to simplify. To simplify, I need a common denominator. Now, you would hope that you could just multiply this by h, but you can't. And you can't even just add h to this. That would just change things. Instead, you do need to multiply both of these by the other's denominator. So I have to multiply this guy by x plus 3. I need to multiply this guy by x plus h plus 3. Let's see what happens. I'll have 2 times the quantity of x plus 3 minus 2 times the quantity of x plus h plus 3 all over my common denominator now of x plus h plus 3 times x plus 3. This is all times 1 over h. Let's simplify. Let's distribute. I get 2x plus 6 minus, now I'm going to distribute this negative just so I can do it all at once. Negative 2x plus negative 2h plus negative 6. All over my common denominator, x plus h plus 3 times x plus 3. All times 1 over h. Now, if everything is right in the world, we will see things cancel. Negative 2x and the 2x. 6 and the negative 6. Leaving me with just negative 2h over this denominator times 1 over h. Well, guess what? This h divided by this h goes away. It's just 1. It cancels. So what I have remaining is a simplified function that I can plug 0 in for h. I have negative 2 over the quantity x plus h plus 3 times x plus 3. Plug in 0 in for h. I get negative 2 over, this would be x plus 3 times x plus 3, that's x plus 3 squared. This is my derivative function. This is my slope generator function. I can use that to find the slope of my tangents to my function when x equals 3. And we're talking about my original function. Plug in 3, get negative 2 over 3 plus 3 squared. That is negative 2 over 9 squared, which is 81. So a very shallow, very small negative slope. I guess if you look at 2 over x plus 3, see if we can think about it graphically. Negative 3 would be a vertical asymptote. If I approach 3 from the right, I would get, or sorry, negative 3 from the right, I'd get a value that was small but positive. So I'd be coming from positive infinity. At 3, I'd get 2 over 6, which is 1/3, so 3 1/3. I'd be coming from positive infinity, so most likely I'd be looking like this. And of course, you can look at the limit at infinity, that's equal to 0, so I'd be getting closer and closer to 0. So this would be the right side of this function. If I think about it at x equals 3, I can see my tangent is very negative, well, it's not very, it's very shallow and negative. Negative 2 over 81. Okay? Sometimes it helps to see visually what that tangent slope needs to be for your answers to make sense. Okay? Your homework will be more examples of finding the derivatives at values and producing equations of tangent lines. So make sure you do that. And this video will be up, hopefully, and it won't be too long so that YouTube doesn't kick it off or anything, and we'll be good to go. Thank you.